All right, so your do now is a good lead-in terms of what we're going to be doing today with the periodic table. And the do now finished up with a question on main group, representative, which is synonymous, and transition elements. So as you said earlier, elements that are in the S or P blocks are main group elements. Elements in the D block are transition elements, and in the F block, inner transition elements. So for example, if you consider this periodic table shown here, main group elements would be S and P. The D block are your transition elements, and then down here you would find your inner transition elements. This periodic table is a little funky because they yank out right there. I don't know. Yeah, they do it the same way here, so it's kind of funky there. It's a little misleading, but I don't think it'll be any big deal. All right, and I don't think we have to write and draw more. I think you're pretty solid with your writing electron configs, longhand, shorthand. You're good. We worked on that whole thing last time. You don't need to know the exceptions to the Aufbau principle. I'm going to mention one of them because I think it will help you understand why silver has a 1+ charge as an ion, but you don't need to memorize these, so sit back and just appreciate it. For example, silver, if you looked at the periodic table for silver, what would you predict is the shorthand config for silver? Krypton, 5s2, 4d9. However, there is evidence from emission spectra as well as magnetic properties that indicate that silver is not this, but rather achieves greater stability with an electron configuration that appears excited because you haven't filled, well, excited, no, that's impossible. Excited is when you don't fill the sub-level before moving to the next, so you violate Aufbau's principle. But when you consider this electron config and you consider silver ion, the ion is formed by removing electrons from the outermost shell first. So the first electron to be removed would be that one. So the ion would be krypton 4d10. And that helps you understand why silver is always 1+, where most transition elements are 2+ and something else. But silver's only 1+. You see these anomalies in the same group as silver. For example, copper can be 1+. You also see it in group 6 with chromium and molybdenum. Zinc would just be argon 4s2 3d10. Okay? So there's actually greater stability by not completing the S subshell before moving to the D, and you have greater stability with a complete D subshell than you do the outermost subshell. You don't need to know the exceptions. They're listed in your notes, and primarily you do see them in group 6 and group 11. But that just helps to explain silver. All right, also here, you know that valence electrons, we talked about it the other day, are electrons in the outermost shell, highest value of N. It's going to be the number after the bracket of the noble gas in shorthand. There's some old versus new nomenclature. You know that there are 18 groups on the periodic table, and the main group elements have specific names. Your alkali metals in group 1, your alkaline earth metals in group 2. Alkali metals are named as such because these metals, when they react with water, form basic solutions, as do these. many of these metals are found in the Earth's structure, if you will, in the crust. And I don't know, Sam and I were talking about this the other day because she had to know which elements were where. And you'd see there was quite a bit of magnesium and calcium, and that helped explain it. Aluminum, group 13, carbon, group 14, nitrogen or pnictogen family, group 15, oxygen or chalcogen family, group 16, your halogens in group 17, and your noble gases in group 18. You'll remember that group 1 and 2 have 2 valence electrons respectively. When you get into the double-digit group numbers in the P block, the number of valence electrons are the back number of the group number. So there's nothing new there. Core electrons you would have heard of last year. Let's make sure you truly understand what they are. And I've got a second POGO packet on advanced periodic trends that I think will help you tremendously. Your core electrons are the electrons that are not valence electrons. So these are electrons in the innermost shell, not the outermost shell. So the innermost shells. So for example, lithium is 1s2, 2s1. We know it has 1 valence electron. It has 3 electrons in total. It has 2 core electrons. So you can just do the atomic number minus the number of valence electrons to get core. So for example, magnesium has 2 valence electrons, the electrons in the 3s subshell. And how many core electrons does it have? 10, 12 minus 2. Let's take a closer look at vanadium, because I'd also like to remind you of some basic nomenclature that you would have learned in honors. If we consider vanadium, vanadium is 1s2, 2s2, two p6, 3s2, 3p6, 4s2, 3d3. There are a lot of things we should consider. First, the valence electrons. How many valence electrons? 2. Don't fall into that trap. Outermost shell is the 4th. There are 2 valence electrons. And vanadium has an atomic number of 23. So right away, if there are 2 valence electrons, you know that there are 21 core electrons. The other point I want to drive home is each of these is a subshell. So there are 1, 2, 3, 4, 5, 6, 7 subshells. This subshell makes up the first shell. These 2 subshells make up the second shell. These 3 subshells make up the third shell. And this 1 subshell is the 4th shell in terms of vanadium. Familiar with all of that, correct? Yes, yes? Violet, yes, yes? Okay. The 3D subshell has how many orbitals? 5. And in this case, you have 1, 2, 3 unpaired electrons. So the circle is the orbital, and that is an electron. Yep.
We have to draw the entire thing out.
I don't think so. The only thing I will say is that if they ask you how many unpaired electrons, you may have to illustrate the last subshell, but no, it's not a, you're not going to have a little drawing contest. Okay?
All
right.
That wasn't the last subshell, though, right?
Say what?
That wasn't the last subshell.
This subshell has the highest energy, but it's not the outermost shell.
Okay.
And if it asked you how many electrons were in the third shell, how many?
None. No, outermost two, my bad.
2 plus 6 is,
8.
plus 3 more is,
I thought you said outermost.
so 11 electrons in the third shell. Okay? And the last one up there was gallium. And gallium, I'm going to switch screens. Be careful on gallium. How many valence electrons for gallium? 3 is correct, the S and the P's. So core would be what? Gallium has an atomic number of 31. 28 is correct. All right? Not a problem there. We already mentioned the S and P block, the D block, the F block. Remember, the number before F is always 2 less than the row you are in. And you will recall that this row here represents your lanthanide series, your 4F, and this row here represents your actinide series, 5F. And again, all review from honors. In honors, you would have learned how to write electron configurations for ions that form from S and P block elements. But I know, for example, I didn't do the D blockers, so we're going to take a look at that. When you form ions, you always strip first from the outermost shell. Now, D block elements have the ability to form ions with multiple charges because in addition to losing from the S, they also can lose from the D, and that's what we want to look at here. So the magnesium example is very simplistic, as is the chlorine. So chlorine is neon 3s2, 3p5. Chlorine's in group 17. 7 valence electrons. It will gain 1 to form a chloride ion. And now instead of 5 electrons in the 3p subshell, you'll have 6. And now you have the same electron configuration as argon, and we say chloride ion and argon are isoelectronic. Keep in mind though, ions can be isoelectronic with each other. For example, if we stay, that's not working, if we stay with this one, we can find a whole bunch that are isoelectronic. So for example, we said chloride ion. I wrote 1 minus, you would typically write just minus. I was trying to fix it, but it didn't work. If you did sulfide ion, if you did argon, if you did potassium, if you did calcium, all of these are isoelectronic. They all have the same electron configuration. Iso, same electronic, electron config. So in this case, chlorine's gained 1 to make the chloride ion, sulfur's gained 2 to make the sulfide ion, potassium has lost 1 to make a potassium ion, etc. So when you form a cation, you lose electrons from the outermost shell first. So magnesium is here as well. You can lose the electrons from the 3s subshell, and now all you have would be the electron config of neon. Here's where it gets a little murky and a little newer. Not difficult, just new. So vanadium is argon 4s2, 3d3. Vanadium 2 ion loses the electrons from the outermost shell. We're going to get rid of those 2 electrons and we have vanadium 2 ion, argon 3d3. The transition elements have the ability to lose electrons from the d orbitals as well. So if you have a vanadium 3 ion, you're going to lose one of the electrons from the 3d subshell as well as these two. And you have argon 3d3. And if you have vanadium 4 plus, you lose those two first and then two of these, and you get argon 3d1. So for example, if you have iron 3 plus, what would be your electron configuration? Right, because you would lose these two, and then you would take one from here. Does that make sense? Okay, so nickel, we know, is what? Argon.
4s2 3d8.
Okay, so a nickel 2 ion is?
Argon.
We're going to get rid of the electrons in 4s. But what if you had nickel 3 plus? Okay? Every year we see a simple question like this, and every year the kids do it wrong. It's so straightforward. The test is so challenging. There's so much material on it. You have to be strong with the very simplistic stuff. Don't let it overwhelm you. It's not difficult. All right, tin is going to be the trickiest of the bunch. Krypton.
That is 2, 4d10, 35p10.
You got it. Oopsie. I had spazziness.
I don't know how to do that.
It's actually very easy. Control plus gives you a subscript, and Control Shift plus gives you a superscript. Alternatively, on these top buttons up here, if you don't have them on your screen, you can easily add them. But it's good to know for chem, especially if you're writing an equation or something. That's the one thing I hate about Plickers, is that you can't use those shortcut keys, and it's so complicated to use superscripts and subscripts. And then Google Forms, which I've been writing a lot of quizzes in for honors, is also equally as
Why don't you write it in Word first?
annoying. When you copy it, it just puts it regular size.
Even if you go into the little
Yep.
keyboard? Wow.
All right, tin 2 plus, be very careful here.
You take the p's.
You take the P's first, right? And then tin 4 plus, what would you take? The P's and the S's. So this is very, very easy. You're very good at it. Couple little homework problems and you should be golden, right?
It's P because it's the outermost, right?
And you'll see how subshells really do split when we talk about it on Tuesday. And that'll be an AP topic, not an honors topic. Alrighty, so far so good? Here's another new component, but again, nothing that's going to be terribly difficult, so just have a little patience with it. Electrons are negative, and each electron actually creates a magnetic field, essentially acting as a little magnet. When you pair electrons, whether it be in an atom, ion, or molecule, the substance is weakly repelled by a magnetic field, and we say it's diamagnetic. Di means two, a pair is two. However, if you have unpaired electrons, they are attracted into a magnetic field, and we say the species is paramagnetic. Which groups on the periodic table consist of diamagnetic elements? All paired electrons. Group 2 for sure.
Group 14. Why is it
Some of you are cockeyed with your math.
paired?
All paired electrons.
Oh, there's a group 3.
Group 12,
Wow.
right? Because that zinc would be argon. 4s2, 3d10. Everything would be paired.
Oh.
Oh. Why
Okay.
wouldn't manganese be all paired?
Because
Now, manganese is a funky thing because you're going to say that it's 4s2, 3d5.
Yeah.
It turns out it's actually 4s1. I take that back. Manganese is correct. 4s2. Well, it's chromium that's funky, not manganese. But manganese, yes, is argon 4s2, 3d5. So with 3d5, they're all unpaired in the 3d subshell, right? Singles, because of Hund's rule. Chromium's a little funky. That's one of those anomalies, but it's still paramagnetic. So diamagnetic here, and then what other group would be diamagnetic?
18.
18 for sure, because you're ending in P6.
P6.
You got it.
Are you doing anything with
And
F?
would Lawrencium and Lutetium
Yeah. Would you be
also
doing
be?
those?
Well,
Those would be complete.
be careful there. With your F block, you can't count F1, F2, F3, blah, 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 because this periodic table is a little bit funky.
Terbium and
Yeah, it's,
nobelium?
yeah, it would be. It's kind of tricky here. The F block, the way this is written, is funny because lanthanum is really xenon 6s1, 5d1. It's in the D block,
Yeah.
even though it doesn't look like it here. And then once you get here, then you just say 6s2, 4f3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it'd be these guys. If I can't imagine they would ask you that. That would be ridiculous.
Are you like on a test? Would we
No.
send them
If they're not going to ask you it in May, I certainly will not torture you with it.
What do we know in this group 2?
Only JJ will get tortured.
No.
I'm just kidding. I said it on film too. All right. Which of the following are expected to exhibit paramagnetism? All right. Potassium, without even looking at the periodic table, you know is in group 1, so that is paramagnetic. Mercury. Mercury is a
Group 1 is paramagnetic.
Mercury is a diatomic, right? Group 12. So that's not paramagnetic. What about barium ion? It's lost to,
Oh,
So it's
Oh.
still
yeah.
so it's going to back up to, let's back up, 1, 2, now it's dia, right? Does that make sense?
For which one?
Barium
Okay.
ion. Nitrogen,
Yes.
that would be para. Fluoride ion, that would be dia. It's gained 1 and it's now isoelectronic with what? Neon is correct. Titanium 2+, be careful. It's still para. It loses the electrons in 4s and it still ends in 3d2, right?
Oh.
Yeah, careful, careful. Sneaky, sneaky. Copper 2+. That's going to be para.
Wait, so which ones are
Yeah, what's that
diamagnetic, did we say? For the groups.
Group 2, Group 12, Group 18. The end of the P, the end of the D, the end of the S, the end of the D, the end of the P.
Everything else is para?
Well, there'd be 2 others in the F block, but we're
Yeah.
not going to go
Okay,
there.
disregarding those, everything else is para.
Except you, yes.
Uh,
All right. So our main focus today is going to be on the trends. A lot of this is review from last year. It is.
Do we have to memorize the explanations again?
Everything.
Like, is it?
And some of you may not have gone into great detail with your explanations, so we're going to get you there today. Some of you know how to explain this inside and out. In addition, there are some anomalies that we're going to touch upon. Okay? Now, let's just get a feel for what you remember. I think you'll be surprised. I also just want to indicate that explaining can be very challenging. If they ever give you data, use data in your explanation. Raise your hand if you know how to wrap a present. Okay. Could you explain how to wrap that present to somebody who's never wrapped before?
Yes.
Really? Go ahead, JJ.
Okay, so you get your wrapping paper, you will set her down on the ground, put a present in the middle of it, alright? And then you want to make sure you have tape by you, alright? So you're going to get one end closest to you, you're going to grab the two edges, you're going to bring it up, and at the same time grabbing the other two edges.
You never cut the paper, though.
Do you have that kind of?
Do you have all pre-cut paper?
Okay.
Okay.
I wasn't. You had to go to the store, buy the roll.
Yeah. You already have a roll on the test kit and you have tape.
Well, you just told me to cut it now.
Yes, but it doesn't come pre-cut.
Okay, fine. Cut it. Alright.
You just cut it any size?
You could cut it
It has to be
bigger than the toy or whatever you're at. I was thinking a toy.
Just on one side?
You place it on all
Oh,
sides.
it's hard to explain, is it not?
Toward, take the roll and like push the
It pushed
Yeah, you
towards
have to push
the
it over.
end where the roll is, and then you pick the roll up that
technically are
says the
supposed
paper
to
and
like
roll over,
roll
over,
over.
go over the other side so that you can take the roll.
My rap jobs are.
And then that's where you
They get it done.
That's good. I just put it in the bag, put tissue paper. Perfect.
And that's much easier.
It's so pretty.
But I'm not good at putting tissue paper in.
Put it inside.
Like, underneath, and then you put
That's what Violet just said. So it's not easy to explain how to do something because very often there are 20 steps.
Yeah.
Think about it. Did you know how to go brush your teeth by the time you were 5?
Yes.
Wow. Really?
Yeah, no.
Can't remember.
But if you had to explain to a little kid how to brush their teeth, including put the toothbrush down, put the toothpaste on,
Just a tiny bit, not too much.
right, but also we forgot to uncap it and recap it, otherwise little kids,
How else did you get that out?
I mean little kids, you give a thing of toothpaste and they'll just paint your bathroom. So it's very, very challenging to explain how to do something, okay? Alright, here's your periodic table. The reason why you find explanations in chemistry difficult is because it's hard to explain how to do a lot of very basic things, never mind something that's so complicated. Now, as you go across the period, and across the period is from left to right, the atomic radius decreases. Right, so right away you know as you go down they typically act oppositely, the radius increases. See, you do remember a lot.
I don't.
Alright, it's just gonna, what was the next? Let's name the next thing because then I get to something with the Z effectiveness, like it
What is Z effectiveness?
I don't remember. Ability to strip an electron. The ability to strip an electron.
That's ionization
Okay,
energy.
that's ionization.
Z effective is the effective nuclear
Not there yet.
charge. The effective nuclear charge, and we need to go over that. But as you go across a period, the effective nuclear charge increases. That's what the valence electrons feel in regard to their being drawn toward the nucleus. So if the effective nuclear charge increases, then the valence electrons are drawn tighter to the nucleus and the radius shrinks. Now, as that radius shrinks, we know ionization energy
Well,
increases.
It's easier.
Ionization energy is the ability to strip an electron from the outermost shell. So as you're drawing them tighter, you need more energy to strip it from the outermost shell.
You need more if it's closer?
Yeah.
Yes. Put it this way. That gets back to, you remember the fight in the courtyard?
No.
All right, I'll do that in a sec. I'll do it.
If you have more people, you have to like pluck them around.
Well, go through there.
We'll go through everything. All right? But in terms of your trends, the effective nuclear charge increases. I'm going to put this together for you, and then we're going to go through the explanations in great detail. The ionization energy, which is the energy required to strip an electron from the outermost shell, making a cation, increases. The electronegativity increases. That's the ability of a bonded atom to attract electrons to itself. And the electron affinity, the ability of an atom to attract and hold an electron. That's the energy required to attract and hold an electron. We'll go through all of it. Trends, say it again.
Isn't there more? I guess there's another one.
You can do metallic nature
Yeah, okay,
decreases going across. You want to throw that one in too?
Sure.
The trends work oppositely, going down. The radius gets larger. The ionization energy decreases. The electronegativity decreases. The electron affinity decreases. And we'll briefly mention why and then go into much more detail. As you go down a group, what happens to your shell number? It increases. So you get an increase in the N, or the number of shells. As electrons that are valence electrons get farther from the nucleus, the effective nuclear charge down a group is the same. The shell number increases and electron shielding increases, and we'll explain this as well.
So that was the plucking that I was talking about.
Well, the shielding, the greater the shielding, the easier the plucking. She said it. No, don't use words like that on the exam, please. Don't be like plucking. Where's the chicken? Don't do that. All right. Let's go through the radius in great detail, and then we'll hit the others after the break. But if you would rather, this is your call. I will gladly explain as much as you want. I've got a POGL packet to leave you with over the weekend. If you think you can understand everything from the POGL packet and would prefer to do it that way, that's fine with me.
And then we can ask some questions on Monday.
Never, of course. All right. So, there's a lot of words. But the key to me explaining this one to you is to make sure you understand the logic behind it. Come on, Christian, you can do this. Come on. That's terrible. Don't do that.
Don't do that.
Come on. You run 5K races. We're about 3K in. You're going to roll over on the side and play dead? No. All right. A trend is a predictable change in a particular direction. So we have fashion trends. Boys are still wearing those cargo shorts. girls are wearing those, crop tops with their bellies hanging out. I don't get it, but that's what's popular every year. I don't know. Sam tried to get away with one of those tops the other day. I said, go change before Daddy sees you. All right. The radius of an atom is the atomic radius. Now, radii are difficult to measure because even though we will draw a beautiful atom like this, we know that an atom is not perfectly spherical because electrons are in electron clouds. Those are fuzzy regions. We know Bohr's model fails. Electrons aren't in orbits, but rather orbitals, and there's only a 90% probability that the electron is there. So it's very difficult to find the outer edge of the atom. So typically, and I don't think you even need to know this, but we'll draw it anyway. Typically, you have two atoms next to one another that are bonded together, and you can measure the distance between their nuclei, cut it in half, and you have what?
No, I thought you would ask what it was. I don't know what that is.
What?
It's a plank between two hydrogen atoms.
I think it's an eyeballs.
No.
No, I mean, never mind.
Now it's a table. Another table.
I know what it's
With
called.
a plank on top.
It has a name?
The distance between the nuclei of two hydrogen atoms is a plank.
Really?
Yeah.
Might it be the internuclear distance?
Planck.
Like Planck's constant?
Let me just say it different ways to show
I think so.
No?
You said what? Atomic nuclear distance.
It's called the internuclear distance. Let's look that up. All right.
No, I think the other thing I forgot.
So half the distance is the atomic radius.
Oh, it has, no, you can go, because it had nothing to do with chemistry.
Okay, so we'll hit it during the break. Alrighty. So, chop chop. Here, pick two elements in period 2.
Brilliant.
Beryllium,
Barium.
period 2!
Oh, my bad. Chlorine.
Strontium.
Fluorine's not in
Period two, sorry.
Yes, it is. Smart kids only make the same mistake one time. Alright. Smart kids never make the same mistake more than once. That's silly. Alright.
That's a lie.
Really?
Whoa.
Yeah.
Make the same mistake.
Not over and over again. They don't make the same mistake again and again.
Sometimes.
Except my daughter who never cleans up her room.
Ooh,
Alright.
so bad on
If they don't understand the concept of what they do,
My mom was
then
like,
mistake over and over again until they learn.
Okay. Beryllium. Come on, guys. Gotta focus. It's Friday. Here we go.
oh,
Beryllium. 4 protons, 5 neutrons. This first ring here, which isn't very good, represents n equals 1. And the second ring here represents n equals 2. In the first shell, we have 2 electrons, and in the second shell, we have 2 electrons, which are valence electrons. Yes, yes? Chop, chop. Here we have 9 protons and 10 neutrons. First shell, second shell. Circles are a little lacking today. In the first shell, we have 1, 2 core electrons. 1, 2, 3, 4, 5, 6, 7 valence electrons. Valence, tomato, tomato. Okay. The effective nuclear charge, also sometimes called core charge, will increase as you go across the periodic table. The effective nuclear charge is abbreviated Z effective because Z represents the atomic number, which is equal to the number of protons. The effective nuclear charge is what the valence electrons feel in regard to being drawn toward the nucleus. So the effective nuclear charge is the number of protons minus the number of core electrons. So for beryllium, the effective nuclear charge is 4 pluses minus the 2 core electrons, and that's going to be equal to 2 plus. And for fluorine, it's going to be 6 positives minus 2 is 4 positive. That's terrible addition. Don't look at that. I can't believe I did that. So it shouldn't have been 6 positive. It should have been what? Ding dong. 9, right? And 9 minus 2 is 7. Dummy. I don't know where I got it from. Stupid land. Don't even know where I came up with that one because there's no 6 on the page. Duh. That's all right. We've all demonstrated we're human. All right. Are you clear there? I apologize. Dingbat-itis. Okay. As we go across the period, we see that the effective nuclear charge increases. And the valence electrons are drawn more tightly or tighter to the nucleus. And as a result, as you go across the period, the atomic radius decreases. When you write it up, fluorine has a smaller atomic radius than beryllium because it has a greater effective nuclear charge. The valence electrons are drawn tighter to the nucleus, hence the radius shrinks. Okay? It's all there. It's all there. You will see some leveling off toward the end of the period. Toward the end of the period, there is tremendous electron-electron repulsion. You're stuffing 8 valence electrons in the outermost shell, and as a result, you will see some repulsion. So you may not see group 18 following the trend. It's difficult to predict. They would be more apt to show you that it didn't occur. And we can look at the radii for the elements on the periodic table. Come on, baby. Where are you? Come here. There it is. So if you looked at it here, you can see across period 2, the radius shrinks, shown by these values here, probably in picometers. But then neon, you see a slight increase. You see decrease, 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 decrease. But again, here you do see an increase right there. They're not going to ask which ones do that. They'd be more apt to say something, you know, as you go across the periodic table for period 2, you note that there's a decrease in the atomic radius, yet neon has a larger radius than that of fluorine. Why? And that would be electron-electron repulsion as opposed to the increase in effective nuclear charge. So read the question carefully in case they show you something that you wouldn't normally predict. All right, last piece before the break. When we go down a group, yes?
Do transition elements follow that rule?
Transition elements are a little bit funky because you're actually throwing more and more electrons into the previous shell, if you will. And so sometimes shielding has an effect and you don't see as big of a trend, and they usually won't ask you to compare those. That's a good question. All right, now down a group, let's make a comparison. Pick 2 elements in group 2.
Lithium? No, I
Two.
didn't.
Calcium.
You want to do magnesium and calcium? Can I do beryllium and calcium? They'll just show it a little better.
Yes.
I was doing strong.
Do beryllium and
No, it's too
barium.
much to
Do
draw.
barium.
7th hour on Friday. Beryllium
Barium.
and calcium. Now, if you can't write electron configurations, this one's going to get cut off. Like the back of your hand, you have a lot of work to do this weekend. You got to be great at this. Beryllium has 4 protons and 5 neutrons. First shell, valence shell, just as we did previously. And we've got 20 protons and 20 neutrons. You can see it visually. So you have 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. I didn't draw this valence shell in pink. I just got so caught up in my circles.
It's okay.
You're good with it?
You forgive me.
I'll do the valence electrons in pink. Here, I'll put this one in blue so it looks the same and you don't get upset. Because I see JJ's getting upset. All right. So you can see clearly as you go down a group, the atomic radius increases. And that's because the valence electrons are in the 4th shell as compared to the 2nd shell, farther from the nucleus with more electron shielding. The core electrons act as a shield, preventing the nucleus from drawing those valence electrons in. There's no change in the effective nuclear charge going down a group. In fact, the effective nuclear charge is equal to the number of valence electrons. Group 2 has an effective nuclear charge of 2. With electron shielding, we'll go through this a couple different ways. This is JJ's example.
Yeah.
Here's your offensive line. Here's your defensive line. Quarterback took his offensive lineman out to dinner the night before the game because their role, JJ, is what?
Block.
Block whom?
The defensive line and the defense in general.
And who are they trying to protect?
The quarterback.
The quarterback. So the offensive linemen act as a shield, preventing the defensive lineman from getting to the quarterback. The quarterback never wants the back of his jersey dirty because that means he got sacked, fell on his hiney, and then right on his back. And usually when a team wins the Super Bowl, the quarterback goes out and buys his offensive lineman very nice presents, usually Rolex watches. Why not? They have more money than they know what to do with.
Exactly.
Now, shielding is also important at concerts, baseball games, anywhere. So you go to the concert, and the performer's on the stage. He actually looks like he's in a fishbowl, but whatever. And here are all the adoring fans, otherwise known as lunatics. And where do the police go? Right here, because they act as a shield, right? And you want to see what happens if you don't have a shield? Have you ever seen a field stormed like crazy? Have you? All right, it's fun to watch. You want to see? All right, I'll show you. Did I show you the video?
What video?
No, I didn't show this video last year. This is great.
I threw them away. I threw them away. Too much sauce.
This is the best. You want to see? Brendan's going to like this the most. Now, usually, you're at a ball game. Where are the cops? Everywhere. And in the 9th inning, they are positioned on the dugout, around the dugout, protecting their players. But not in New York in 1976. Watch what happens. Now watch where the cops are. The cops are right here. They weren't ready. There's no shield, and look what happens. Only in New York. These are crazy fans. Never touches home plate. See, the shield's broken. Now they're trying. See, the cops should have been up here.
Wait, so we never had home plate?
No, somebody stole it. This is New York. Get real. Of course. It was fun. All right. They destroyed the field. They couldn't even, they had to get it ready. You know, years ago, they didn't have all the playoff rounds that we have now. They just had a 5-game, like the American Conference was just 2 divisions, not 3 like it is now. So they played off a 5-game series, and then who won that played against the National League winner in a 7. So when you hear about like Mr. October, that's when the World Series used to be, and now the World Series falls into November a lot because it's all prolonged, and they didn't cut the number of games. They're still at 162. But in any event, what you can see clearly as you go down a group, the radius increases because the valence electrons are farther from the nucleus with more electron shielding. And these concepts are critically important. We're going to take a 5-minute break. Keep in mind the video is running, so watch your conversation. And we'll pick up with 2 other pieces, and then we'll get you started on the POGL, unless you just want to do the POGL.
So is that ionization or?
Huh?
When you refer to that, are you referring to ionization?
What do you mean ionization?
When you're talking about that, it's the shielding.
The shielding affects the radius, the ionization energy, and the electron affinity down a group. And we'll clean that up after the break.
Yeah, it's your fault.
These are open today.
Wow. Yeah, she did.
I believe everyone.
Oh, I didn't make cookies.
It's extra.
I'll take it. I'll take it.
I know.
I got 2 A's ago.
All right, we'll have to update it.
I got back on track.
What's the matter, baby? You're so tired today. You're so down.
been a long week. I've had to practice every single day.
Here you go, Dr. Kayla.
It's
Blank, blank.
So even though I'm lost a lot of sleep, then most high schoolers
so you're just pooped. But this is not internuclear distance.
Not.
No. It's just a unit of length, and that's a constant. Whereas the distance between the nuclei of two atoms is not constant.
I think it's the distance between the what is it called?
Is it only for hydrogen?
I think it's between two hydrogen atoms, yeah. I could be wrong.
Maybe it is.
I don't know if they
Guys, I'm gonna put this on YouTube.
I know. It's okay though.
I'm not consenting to me being recorded on video.
That's illegal.
I'm joking, I am.
No, he's not. Mine. I really like to say a bad word right there.
and then what's next? That's what I would Oh yeah. And then you. Yeah.
So wait.
We never actually really did.
Yeah, and I write pretty. I'm very good at editing. I'll edit it for you. Writing from scratch. I made my husband do this.
No, they only need 6 for the application. Like besides the main essay, they require no. They all require the main essay.
When you find out when you're is it like in January or February? A month? Oh. Is it the earlier you do it, or is it about the same
Yeah, so fancy requires
Well, I'm glad I don't have to worry about that till next year. Because I just can't.
Right now, but since you know the application, what else is there? You have your classes and it's Oh. Yeah, you're right. It's English. I don't find your watch.
Alright, Dr. Kalish, I got another thing.
Okay.
It says a hydrogen atom is about 10 trillion blank lengths across. So about the.
Are you sure? Divided by 2. And then is it what you said? When you said, is it hydrogen atom is all the way across, or divided by 2?
Oh, I don't know.
It's small. It's very small. We usually do radii in picometers. Pica is small. Figure out how much it is in a meter. All right, let's be seated.
Oh, it says on here how many meters it is.
A picometer is what? 1 times 10 to the 12th?
Yeah.
Yeah.
This is 1.616 times 10 to the negative 35.
Teeny.
To join
Yeah, Monday, very much.
I'm coming.
But, yeah, but you can't leave the building on Monday. Otherwise, I can do the meetings in the morning or after school. You just have to decide. You just can't leave the building and get back in. I can't write that many lunch passes. So make sure you have your lunch that day. All right, let's go, let's go.
When we work on the focal packet,
In a little bit. You want to do it now? I know. We'll get you there soon. All right, guys, come on. Let's go for 10 more minutes, and then I'll let you work on the Pogo packet. Maybe 15. No whining. All righty.
What point do we have to get to?
You like my ring?
Alrighty, with ionic radius, you're talking about the radius of an ion. Come on, guys. And let's think about this.
Okay.
If, for example, I had sodium, 1s2, 2s2, 2p6, 3s1, and I had a sodium ion, I would lose the electron from the outermost shell. What would you guess has a larger radius, sodium or sodium ion? Sodium, because it has an electron in the third shell farther from the nucleus with more electron shielding, where the ion now only has electrons into the second shell. Okay?
yeah, it takes it back. It goes back. Like if you were to look at it.
It goes back to the noble gas in the previous shell. In contrast, if you formed a cation, and this is a little bit tricky, don't yell out the answer right away. Let's think it through. Anion. Cation?
Yeah, you said cation.
You said
Can you
cation.
form the cation?
Oh, well, we just formed the cation. Now if we form an anion, I'm sorry. Now, why is the effective nuclear charge for fluorine and fluoride ion the same?
'Cause it's
Have we changed the protons? Have we changed the number of core electrons? No. So an atom and an anion have the same effective nuclear charge. But you've added an electron to the second shell. But you don't have as much positive charge to counteract that additional electron. You have the same effective nuclear charge as you had for the element. And as a result, the radius of the anion is larger for two reasons. The effective nuclear charge acting on more electrons is less. Let me restate that. The effective nuclear charge acting on more electrons is the same, and you've added another electron to the shell, which introduces more electron-electron repulsion. They push off one another, and the radius grows. So an anion is always larger than the corresponding element because the effective nuclear charge is the same. And you introduce electron-electron repulsion, and this is written in your notes. Whereas a cation will always be smaller than its corresponding element because it's lost the electron or electrons from the outermost shell, and as a result, the radius will be smaller because you don't have electrons distanced as far from the nucleus. The only other piece that may be a little challenging in regard to this, and I don't really think you'll see much of this, but I'll show you one example here, is if you have a whole bunch of isoelectronic species, you will find the more negative the ion, the larger the radius, the more positive ion, the smaller the radius. So what you'll find here is uridium ion is the smallest, then strontium ion, rubidium ion, then bromide ion, then selenide ion. So the more negative, the larger, the more positive, the smaller. And again, I don't think you'll see that. I wouldn't sweat it. All right, in regard to the trends we want to examine, we looked at the radius. We know as you go across the periodic table, the atomic radius decreases because of the increase in the effective nuclear charge. So the radius gets smaller. We know as you go down a group, the radius increases because electrons are in higher principal energy levels, farther from the nucleus, with more electron shielding. Okay. Electron affinity is the energy that is released in almost all cases when an electron is added to a gaseous atom. So it's the ability of an atom to attract and hold an electron it didn't have previously. When you attract an electron, if you were initially neutral, what charge will you be? Negative. So sometimes it can look funny. Here it looks pretty typical. But don't get upset because you could have sodium attracting an electron and all of a sudden sodium would be negative, which is not what you would typically see, so don't let it bother you. So electron affinity here illustrates exothermic. That's the energy that is released by attracting and holding an electron in the case of fluorine, and it's very, very high. In general, we find the electron affinity increases across a period. As the effective nuclear charge increases, the more positive you will be, then the ability to attract and hold an electron increases as well, since opposites attract. Generally speaking, as you go across a period. Now, I put this diagram in after I posted your notes. I apologize. Let's take a look at it. This is not typically what they ask you. They typically go for ionization energy. But if we, let me see if I can put a box here. It may block it out. Let me see. All right, so if we focus now on, yeah, that's not going to work. If we focus now on not on group 2, on period 2, we've got lithium, beryllium, boron. Can you see this, or you want it bigger? Is that beautiful?
Yes.
All right. We've got lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So let me see if I can do this. Generally speaking, if you consider fluorine, oxygen, carbon, and boron, you can see that the electron affinity increases across a period. Explanation, the effective nuclear charge increases, the ability to attract and hold an electron increases as well. Now, they do become more exothermic, more negative, so you're really looking at the absolute value when you consider increasing. However, what do you see in this period that is against that norm? You see nitrogen, from carbon to nitrogen you go down. So it decreases, and you see it for lithium to beryllium as well. So we want to look at beryllium and nitrogen and what's so unusual about those. It's all written out for you. I want you to see it so you truly understand what's going on. All right, so beryllium is 1s2, 2s2. And right now beryllium doesn't have an electron in the 2px orbital. This would be 2px, 2py, 2pz for the axes. Okay, so if beryllium was going to attract and hold an electron, it would form a beryllium ion as such. And where would we stick the electron? 2px, right here. So beryllium has a very low electron affinity. It's actually endothermic because it has little tendency to acquire that electron. It would have to gain it to the 2px orbital. And what you will see when we talk about PES is there is a binding energy for electrons in a subshell. And the binding energy for this electron to the 2p subshell is considerably less than this. And it is extremely unfavorable. Don't write it's unfavorable. We're going to get into this in regard to the binding energy when we talk about PES on Wednesday or Tuesday. For right now, it would have to attract the electron to the 2px orbital, which is farther from the nucleus with lower binding energy. The nitrogen aspect is interesting as well. Nitrogen is 1s2, 2s2, 2p3. And when nitrogen gains the electron, it would form this ion. And where would that electron need to go? It'd go into the 2px orbital. And now you've introduced electron-electron repulsion, which is not favorable. And as a result, you can see that the electron affinity for nitrogen is less than what you would predict because of the unfavorability of gaining the electron to the 2px orbital because of the introduction of electron-electron repulsion. So you see these anomalies, these irregularities in electron affinity in groups 2 and 15 for different reasons. And you only see them there. It's tricky. That's the anomaly piece. Your book is not great in its explanations. You can read it, but it's not great. The other thing I want to mention is if you have beryllium and calcium, what is electron affinity? The ability to attract and hold electron, an electron you didn't have previously. So for example, why do you see a decrease in electron affinity? This will be our new electron as you go down a group. The electron would be attracted to a higher principal energy level, farther from the nucleus with more electron shielding. So the ability to attract and hold would be less. And if you understand the concept, you don't have to memorize and you're not going to break down on it. That's a trend you learned last year. The other thing you really want to make sure you can do is explain. Can you explain? Here are two problems right here. The second one is super easy. Let's do that together. The second one says, explain why the electron affinity of nitrogen is greater than that of antimony. Why would nitrogen have a greater electron affinity? All right, well, be careful. Let's be very, very, very specific. So nitrogen would be attracting and holding the electron to which shell? Nitrogen's in what period? 2. The second shell, closer to the nucleus with less electron shielding. So its ability to attract and hold an electron is considerably higher than that of antimony, because where would antimony be looking to attract and hold it? To what shell? The 5th, because it's in period 5. So that's what we're going to work on, and I'm going to put some horrible explanation up here next time, and you're going to fix it. The other question is the AP level style. Explain why the electron affinity of N is less than that of carbon, and that's not what you would predict by the trend. So what is it about N? Because you would be attracting and holding it to the, be specific on it, to the 2px orbital, which introduces electron-electron repulsion. You could say you would be attracting it and holding it to an already occupied 2px orbital, which introduces electron-electron repulsion. That's what you're looking at. Yes, you were done 10 minutes ago. So I'm going to give you the POGIL packet.